Dear student, welcome in the class of mathematics. Today we have to see Cauchy Riemann equations. Let u and v be real valued functions of two variables x and y, then the equations ux is equal to vy and ui is equal to minus vx are called Cauchy Riemann equation, shortly CR equations. Here ux means w by x, that is the partial derivative of u with respect to x. Vy means w by y, ui means w by y, and vx means w by x. Now we have to see very important theorem. A necessary condition that a function w is equal to f of z is equal to u of xy plus iv of xy be analytic at point z is equal to x plus iy is that at point xy, real and imaginary parts u and v of the function f of z satisfies CR equations. This is the just necessary condition and not sufficient condition. That is, the converse of this theorem is not true. Means if u and v satisfy CR equations, then function f of z need not be analytic. After the proof of the theorem, we have to see some examples of functions which satisfies CR equations but not analytic. So first, see the proof of the theorem. Let w is equal to f of z is equal to u of xy plus iv of xy be analytic at point z is equal to x plus iy. And therefore, as that function is analytic, its derivative at z is axis, means f dash z is axis. And we know f dash z means limit delta z tends to 0, f of z plus delta z minus f of z upon delta z is axis. As this limit is axis, means limits along different paths is same. And so here we have to consider two paths along a real axis and imaginary axis. So first consider limit along real axis, that is along x-axis. Here z is equal to x plus iy. So delta z is equal to delta x plus I delta y. Here delta x means change in x coordinate and delta y is change in y coordinate. Along real axis, change in y coordinate is 0. And so we get delta z is equal to delta x plus I into 0, which is delta x. So delta z is same as delta x. Now put this in equation number 1, and so we get f dash z is equal to limit delta x tends to 0, f of value of z, which is x plus iy, value of delta z, which is delta x. So this will become f of x plus iy plus delta x minus f of x plus iy upon delta x. Collect here real parts, and so f dash z is equal to limit delta x tends to 0, f of x plus delta x plus iy minus f of x plus iy upon delta x. As f of z is equal to u of xy plus iv of xy, put z is equal to x plus iy, so we get f of x plus iy is equal to u of xy plus iv of xy. Now put x is equal to x plus delta x here, we get f of x plus delta x plus iy is equal to u of x plus delta x y plus iv of x plus delta x y. And so put these two values here, so we get f dash z is equal to limit delta x tends to 0, u of x plus delta x y plus iv of x plus delta x y minus u of xy plus iv of xy upon delta x. So this is equal to limit delta x tends to 0, collect the real parts and imaginary parts. So we get u of x plus delta xy minus u of xy plus iv of x plus delta xy minus v of xy upon delta x. Now separate the denominator here. So this is equal to limit delta x tends to 0, u of x plus delta xy minus u of xy upon delta x plus I outside v of x plus delta xy minus v of xy upon delta x. Now separate limit also, and so this is equal to limit delta x tends to 0, u of x plus delta xy minus u of xy upon delta x plus I outside limit delta x tends to 0, v of x plus delta xy minus v of xy upon delta x. In the first limit, we observe that there is change in x coordinate and y coordinate is fixed. And so this is the partial derivative of u with respect to x. So this is del by u by del by x, xy, or you can say ux xy. Similarly, the second limit, this is the partial derivative of v with respect to x at point xy. So you can say this is del by v by del by x or simply vx xy. And so finally we get f dash z is equal to ux xy plus I vx xy. This is equation number 2. Now consider limit along imaginary axis, that is y-axis, as delta z is equal to delta x plus I delta y. Along imaginary axis means y-axis, change in x coordinate is 0. So we get delta z is equal to delta x, which is 0, 0 plus I delta y, and so we get delta z is equal to I delta y. Now put this in equation number 1, and so we get f dash z is equal to limit I delta y tends to 0, f of x plus iy, I delta y minus f of x plus iy upon I delta y. That is f dash z is equal to limit I delta y tends to 0, f of x plus iy plus I delta y minus f of x plus iy upon I delta y. Transfer this I to this side, and so we get limit delta y tends to 0, f of x plus y plus delta y, collect their imaginary parts, minus f of x plus iy upon I delta y. 1 over I is a constant, so take outside of that limit. So we get 1 upon I limit delta y tends to 0, f of x plus I into the bracket y plus delta y minus f of x plus iy upon delta y. So this is equal to 1 upon I limit delta y tends to 0. Put the value of f of x plus iy, which is u of x plus iv of xy, and value of f of x plus I into the bracket y plus delta y, which is u of x plus y plus delta y plus iv of x comma y plus delta y. So this is equal to 1 upon I limit delta y tends to 0. Collect the real parts and imaginary parts. So this limit is limit delta y tends to 0, u of x y plus delta y minus u of xy plus I v of x comma y plus delta y minus v of xy upon delta y. Now separate denominator. So this is equal to 1 upon I limit delta y tends to 0, u of x comma y plus delta y minus u of xy upon delta y plus I outside v of x comma y plus delta y minus v of xy upon delta y. Now separate the limit also. So this is equal to 1 upon I limit delta y tends to 0, u of x comma y plus delta y minus u of xy upon delta y plus I v of x comma y plus delta y minus v of xy upon delta y. So this is equal to 1 upon I. See this first limit, there is change in y coordinate and x coordinate is fixed. So this is the partial derivative of u with respect to y, that is del by u by del by y, or you can say uyxy plus I into this second limit is vyxy. And so 1 upon I multiply here, multiply and divide by I here. So we get this value is I upon I square. Value of I square is minus 1. So this will become I upon minus 1, that is minus I. And this bracket as it is. So f dash z is equal to minus I uyx comma y plus I v of xy. Now take this minus I inside 1. And so we get f dash z is equal to minus I uyxy and then minus I square vyxy, but value of minus I square is plus 1, and so we get f dash z is equal to minus I uyxy plus vyxy. First write down the real part and then imaginary part, and so we get f dash z is equal to uyxy minus I uyxy. Say this is equation number 3. By equations 2 and 3, we have ux xy plus I vx xy is equal to vyxy minus I uyxy. Take this minus sign inside, and so we get ux xy plus I vx xy is equal to vyxy plus I minus of uyxy. Now comparing real parts and imaginary parts on both sides, we get ux xy is equal to vyxy and vx xy is equal to minus uyxy. Transfer this minus sign to this side, and so we get uxxy is equal to vyxy and uyxy is equal to minus of vxxy. And therefore, real and imaginary parts u and v of that analytic function f of z satisfies the CR equations at point xy. And therefore, if a function f of z equal to u plus I will be analytic at point z is equal to x plus iy, then real and imaginary parts u and v satisfies the CR equations. And hence the proof of the theorem. Remark, the converse of this theorem is not true. So for that, we have to consider some example. So see the first example. Show that the function f of z is equal to root of mod of xy is not analytic at origin, though the CR equations are satisfied at that point. Solution. First, to show real and imaginary parts of a function f of z satisfies CR equations at origin. As f of z is equal to root of mod of xy, you can write this term as root of mod of xy plus I into 0. Say this is u of xy and 0 as a v of xy. So we get f of z is equal to u of xy plus I v of xy. Comparing real and imaginary parts, we get u of xy is equal to root of mod of xy and v of xy is equal to 0. Now we have to find ux at 0, 0 and ui at 0, 0. So for that, as we know, uxxy is equal to limit h tends to 0, u of x plus hy minus u of xy upon h. This gives the partial derivative of u with respect to x at xy. Now put x0, y0. So we get ux0, 0 is equal to limit h tends to 0, u of 0 plus h means h0 minus u of 0, 0 upon h. Now put these two values u of h0 and u of 0, 0. You know, u of xy is the root of mod of xy. Put here x is 0, y is 0, we get u of 0, 0. And put here x is h and y is 0, we get u of h0. So put that both values, and so we get ux0, 0 is equal to limit h tends to 0, root of mod of h into 0 minus root of mod of 0 into 0 upon h. Make this calculation. H into 0 is 0, mod of 0 is 0, root of 0 is 0, so this term is 0, this term is 0 upon h. So this is equal to limit h tends to 0 upon non-zero number, which is 0. Now evaluate this limit. So limit h tends to 0, so we get ux at 0, 0 is equal to 0. Now we have to find uy at 0, 0. So for that, as we know, uyxy is equal to limit k tends to 0, u of x comma y plus k minus u of xy upon k. This gives the partial derivative of u with respect to y at point xy. Now put here x is 0, y is 0, so we get limit k tends to 0, u of 0 comma 0 plus k means k minus u of 0, 0 upon k. Now put the value of u of 0k, u of 0, 0. So this is equal to limit k tends to 0, put x is 0, y is k, we get u of 0k as root of mod of 0 into k. Then minus u of 0, 0, put x0, y0 here, so we get u of 0, 0, which is root of mod of 0 into 0 upon k as it is. Make this calculation, so we get this is equal to limit k tends to 0, 0 minus 0 upon k, 0 upon non-zero number, so this value is 0. Now taking the limit as k tends to 0, this limit is 0, and so we get ui at 0, 0 is 0. Now as vxxy is 0, and therefore partial derivative of v with respect to x, xy is 0, and partial derivative of v with respect to y is also 0. And therefore vx at 0, 0 is 0, put x0, y0. Similarly, vy at 0, 0 is 0. And so we get ux at 0, 0, ux at 0, 0 is equal to vy at 0, 0, and uy at 0, 0 is equal to minus of vx at 0, 0. And therefore, u and v satisfies the CR equations at origin. So real and imaginary part of that given function f of z satisfies the CR equations at origin. Now we have to show f of z is not analytic at that point origin. As we know, f dash z naught is equal to limit z tends to z naught f of z minus f of z naught upon z minus z naught. This limit gives the derivative of f with respect to z at particular point z is equal to z naught. Now put here z naught is equal to 0, and so we get f dash 0 is equal to limit z tends to 0 f of z minus f of 0 upon z minus 0. As we know, f of z is root of mod of xy, and therefore f dash 0 is equal to limit z tends to 0, put the value of f of z, which is root of mod of xy, minus f of 0. F of 0 means value of that function when z is 0. When z is 0, x is 0, y is 0. So value of f of 0 is root of mod of 0 into 0, which is 0. And this z minus 0 means z. Now put the value of z as x plus iy. So we get f dash 0 is equal to limit x plus iy tends to 0, root of mod of xy upon x plus iy. This is equation number 1. Now consider the path y is equal to mx. And so we get f dash 0 is equal to limit x plus I, value of y, mx tends to 0, root of mod of x into mx upon x plus I into mx. And so here x tends to 0 as well as mx tends to 0 means x tends to 0, and therefore finally we can write this limit as limit x tends to 0, root of mod of x square into m upon x as a common 1 plus I into m. Now take this x square outside, and so the f dash 0 is equal to limit x tends to 0, x into root of mod of m upon x into 1 plus I into m. Here x get cancelled, and so we get f dash 0 is equal to limit x tends to 0, root of mod of m upon 1 plus I into m. Now evaluate this limit, and so we get f dash 0 is equal to root of mod of m upon 1 plus I into m. Now here we observe that this value depends on value of m. For different values of m, we have different limits. And therefore, this limit does not exist. That is, limit in the right hand side of equation 1 does not exist, means f dash 0 does not exist. And therefore, given function f of z is not analytic at origin, even though CR equations are satisfied at that point. That was to show in the example. That is, the converse of that theorem is not true. Now see another example. If f of z is equal to xy square into the bracket x plus iy upon x square plus y raised to 4 if z not equal to 0, and this is 0 if z is equal to 0, show that CR equations are satisfied at z equal to 0, but f dash 0 does not exist. Solution. Given f of z is equal to xy square into the bracket x plus iy upon x square plus y raised to 4 if z not equal to 0, and this is 0 if z is equal to 0. As f of z, xy square into the bracket x plus iy upon x square plus y raised to 4. Take this xy square inside 1, and so you get f of z is equal to x square y square plus I x y cube upon x square plus y raised to 4. Separate the denominator. So we get f of z is equal to x square y square upon x square plus y raised to 4 plus I x y cube upon x square plus y raised to 4. Say this is u of xy and this is v of xy, and so we get f of z is equal to u of xy plus I v of xy, u of xy x square upon x square y square upon x square plus y raised to 4, and v of xy x y cube upon x square plus y raised to 4. As we know, ux xy, put x 0 y 0, so we get ux at 0 0 is equal to limit h tends to 0 u of h 0 minus u of 0 0 upon h. Put here x is h, y is 0, we get u of h 0, and put x 0 y 0, we get u of 0 0, and put that both values here. So we get limit h tends to 0, h square into 0 plus h square upon h square plus 0 minus u of 0, 0. U of 0, 0. See here, if z is 0, means x and y both are 0, then value of u is 0 from this. And so put that value 0 here upon h, make this calculation. So limit h tends to 0, 0 minus 0 upon h. So ux at 0, 0 is limit h tends to 0 of 0, and therefore ux at 0, 0 is 0. Now we have to find ui at 0, 0, which is given by limit k tends to 0, u of 0k minus u of 0, 0 upon k. Therefore ui at 0, 0 is equal to limit k tends to 0, u of 0k, put x is 0, y is k. So this term will become 0 into, sorry, here u of 0k, put x is 0, y is k. So u of 0k is equal to 0 into k square upon 0 plus k raised to 4 minus u of 0, 0. Similarly, u of 0, 0, which already find from this one, if z is 0, real part is 0, so 0 upon k. And so this is equal to limit k tends to 0, 0 minus 0 upon k. So ui at 0, 0 is 0. So we find ux at 0, 0, which is 0, ui at 0, 0 is 0. Similarly, you can find vx at 0, 0 and vy at 0, 0. Both that values are 0. And therefore, ux at 0, 0 is same as vy at 0, 0 and ui at 0, 0 is equal to minus of vx at 0, 0. And therefore, real and imaginary part of given function f of z satisfies the CR equations at origin. Now to show f dash 0 does not exist. As you know, derivative of f with respect to z at particular point z equal to z naught is given by limit z tends to z naught f of z minus f of z naught upon z minus z naught. Put z naught is equal to 0, and so we get f dash 0 is equal to limit z tends to 0 f of z minus f of 0 upon z minus 0. So f dash 0 is equal to limit value of z as x plus iy. So limit x plus iy tends to 0, given value of f of z, which is xy square into the bracket x plus iy upon x square plus y raised to 4 minus, he has given f of 0 is 0 upon z means x plus iy. Here we observe that this x plus iy get cancelled, and so f dash 0 is equal to limit x plus iy tends to 0 xy square upon x square plus y raised to 4. This is equation number 1. Now here consider the path y square is equal to mx. That is y is equal to root of mx. And therefore f dash 0 is equal to limit x plus I value of y, which is root of mx, up into the bracket x into value of y square, which is mx, upon x square plus y raised to 4. Take square on this side, we get y raised to 4 is equal to m square x square. And so this is here limit x plus I root of mx tends to 0. So you can write this 0 as 0 plus I 0, equating real and imaginary part. So we get x tends to 0 and root of mx tends to 0. And so root of mx tends to 0 means x tends to 0. And so in both cases we get x tends to 0. So write down only x tends to 0. And therefore x plus I root of mx tends to 0 means x tends to 0. So put this in this limit, and so we get f dash 0 is equal to limit x tends to 0 m into x square upon, take out x square as a common, 1 plus m square. Here x square get cancelled. So f dash 0 is equal to limit x tends to 0 m upon 1 plus m square. Now evaluating this limit, finally we get f dash 0 is equal to m upon 1 plus m square. Now we observe that this value depends on m. For different values of m, we have different limits. That is, this limit does not exist. Means limit in the right hand side of equation 1 does not exist, means f dash 0 does not exist. And therefore, here u and v satisfies the CR equations at origin, means z equal to 0, but f dash 0 does not exist. And therefore, converse of that theorem is not true here also. In the next lecture, we will see some more examples. Thank you.